Welcome, everybody. Welcome to this webinar on Hypershield, the second one we have had so far. We're following the journey of Hypershield. Before we get started, my name is Lars-Erik Bråtveit. I'm the cybersecurity lead here in Norway. I've had the pleasure of having some hands-on with Hypershield as it's developing. So we're working closely together with Cisco here in across all of the Conscia countries, really. So we've had some hands-on experience and are very excited for the product. And right now, I'm waiting with quite a bit of excitement for the new DPU-enabled switch, which will move Hypershield all down to the switch. We are getting an early field trial in Conscia, so maybe the next one will be more in depth on how we do that on the hardware level. With me from Cisco, I have Jeroen and Christian, who are going to be the main people talking. So I'm just going to do a very, very quick intro. First of all, housekeeping. Hopefully everyone can hear me. If you can't hear me, hopefully the visual graphic will get you up and running with the audio. You are muted, as is normal with all the webinars. If you do have any questions, please write them in the Q&A. Christian will monitor that and make sure that those questions get answered. And of course, this webinar is recorded, so when we're done processing the video, you will get a link and you can share that with your friends and family, whoever would have an interest in Hypershield. So, go wild. Just a few words. If you've managed to get into this webinar and not be a Conscia customer, this slide is for you. This is Conscia at a glance. When we last had the Hypershield webinar, I think I just announced that we'd acquired a company in the UK and we've gone into the UK. And since then, we've expanded into Ireland and also into Belgium. So Conscia is a company that is growing. We're a pan-European company. We have excellent people all across Europe, and it changes on a monthly basis. As you can see, we have happy customers. We've got happy employees. We work with very, very mission critical infrastructure with our customers. We've got the really big, cool projects, and our company is very tech heavy. As you can see, over half of our company, they're engineers and analysts. So it's a good place to be for everyone interested in tech. A few words on our technology strategy. So many of you will know Conscia most for their networking expertise, and especially our Cisco networking expertise. But our strategy also moves into the cybersecurity area, and you would say that Hypershield is probably associated with cybersecurity, but also a little bit with hybrid cloud. So we're touching in on both of those, and then of course we have observability, so you're able to observe what's going on and act according to that. To make this happen, we of course work with our strategic technology partners, and right now our main strategic partner Cisco is here, and this is of course what we're going to talk about. So with that, I'm done. Jeroen and Christian, the floor is yours, so I'll stop my sharing and you can just take over.
Yeah, good morning everyone. Thank you for joining this exciting webinar. My name is Christian Heinel. I'm the Security Solutions Engineering Leader for Northern Europe here at Cisco. Together with me, Jeroen will be taking over in just a few seconds, and we will get started. If you have, as Lars-Erik just mentioned, if you have any questions, please use the QA panel. You will find it down to the right in the bottom on the panel. And put them there. Some of them I might answer directly, and some we'll put into to the presentation for everyone to understand the response and answer to those questions. So thank you very much for joining, and enjoy the show. Over to you, Jeroen.
Morning. Thanks for having me. So my name is Jeroen Wittok. I'm a TME, which means I can wear technical hat, marketing hat. Today I'll be wearing mainly my technical hat. We'll be doing an update on Hypershield, as well as towards the end some live demos. So we'll see how that goes. So with that, let's get right in. So the agenda for today is we'll review briefly the architecture. We'll talk about the updates we have as far as the different enforcers go. We'll give a quick review again of the policy model we use. We'll position eBPF and where we use it. We'll talk about AI and the digital twin. And at that point, I will actually skip the distributed exploit protection and autonomous segmentation to have a very brief update on Hypershield API, and then we'll go into live demo where we'll show where we are today with autonomous segmentation and distributed exploit protection. As mentioned, do feel free to ask questions in the Q&A. We'll try to answer them live whenever we have the chance. So one of the things which is new since last time we spoke about Hypershield is that now Cisco is positioning most, if not all, of their security tooling under the umbrella and vision of what's being called hybrid mesh firewall. What that means specifically for Hypershield is that initially not that much, but sure, in the near future actually quite a lot. In what context? Well, because from day one, Hypershield has been a prime citizen of Security Cloud Control, which is like our security control platform, which is cloud-based. And the advantage of being a prime citizen there is that under the new vision of hybrid mesh firewall, there is now a move to start adding more and more with the goal of adding almost everything from a security portfolio hooked into this platform. What that means is that all of these tools, instead of being individual tools, they will start to be able to talk to each other. They will start to be able to exchange configuration, data, events, and all of those things, so that we can get towards a holy grail vision of having like full mesh integration through this single common platform. So if you then dive deeper into Hypershield, some updates since last time we spoke. So the two main goals are, of course, very much still autonomous segmentation and exploit protection, but we've now also added zonal for firewalling, which is mainly made possible through the smart switch that we'll talk about in a minute. We still have the same goals as far as workload and network enforcement, right? So we'll have a combination of enforcers that can live inside of the operating system where your applications run. Today, that's most of the Linux distributions that are not more than 5 to 8 years old. And then Windows is coming pretty soon, right? So Microsoft is in final stages of getting that released. So within a few weeks, a few months at most, that will be there. And then from the network point of view, we also have the capability to deploy some enforcers there. Initially, that was only the VM-based enforcer, so basically a virtual machine that you can deploy at strategic locations to start doing network level policy enforcement. And then now, since Amsterdam, we have also announced our first smart switch, which is essentially a DPU-based switch where we combine the best of both worlds, both from Cisco Silicon for high-performance packet forwarding, and then DPUs, where we can then start introducing additional capabilities, with Hypershield being the first of those capabilities. The beauty of the managed globally, enforced locally, is now reinforced with these smart switches, right? Because when you think about the smart switches, they give us like a hardware platform where we can enforce segmentation policy. You can now have that distributed, right? Because wherever you start introducing those smart switches, you now have hardware-based enforcement points, which gives you the advantage of one, hardware, obviously, and second, you start to introduce a more distributed nature of applying the services. Today, we're focusing on Hypershield security services, obviously, but having like this distributed nature, this hardware nature, also introduces a new challenge, which is, whereas if initially you go from like a centralized security enforcement to a distributed enforcement model, you need to have a management layer that is able to deal with this distributed nature of those enforcement points, which of course for Hypershield is a non-issue, because that's how Hypershield was built in the first place, right? To have like a single global control plane and then a distributed data plane in the form of all these different enforcers. One thing to note is that Hypershield today is very much a SaaS-based offering, but we have taken several steps to start investigating what it would mean or what it would take for us to do an on-prem version as well. That's not an official timeline yet. There's no roadmap for that yet. I just wanted to share with you that this is something that we started looking at. So at some point in the future, I do think that will become a reality as well. So that's on like the big picture, right? So now let's start zooming in into some of the more interesting aspects of Hypershield and how we can make all of this real. So first of all, when we start looking at the enforcers, it might be good to also spend some time on the underlying technology that we use through Överallt, right? So last time we already spoke about eBPF. a lot of the capabilities from Hypershield are actually built based on isovalent capabilities, right? Today, that is mainly the tetragon leg of the isovalent offering, but in the near future, there will be a lot more, right? And one thing that I might perhaps want to update on the slides is that the overlap on Kubernetes seems to be like only a bit, but Kubernetes is actually our main target, right? So the fact that there is overlap, it means exactly that, right? Hypershield is super happy to play in Kubernetes environments, and honestly, it's even the easiest and the most user-friendly to deploy in, because we natively consume all of the typical Kubernetes constructs, right? So the way to look at this is that Tetragon is like the cornerstone of the actual operating system-based endpoint enforcer from Hypershield, right? And through that technology, we actually have like an abstraction layer to deal with eBPF and the capabilities that eBPF brings us, right? Both from a runtime security as well as a networking security point of view, segmentation obviously being the key use case there, right? And then on top of that, with Hypershield, what we will bring is a whole bunch of automation, scale out, single policy management, etc. Now, if for whatever reason you choose to not go with Hypershield and you want to focus on the open source, pure open source technology, the technology which today is also fully on-prem, then you can stick to isovalent enterprise for now. And then at some point you can always choose to go to Hypershield. We are looking to make that journey as seamless as possible, ideally with no effort whatsoever. So when we then zoom in on the actual enforcers, right? So obviously we have the endpoint enforcer, which is running inside the operating system where your workloads are. That is the foundational entry point for Hypershield to start gaining insights and intelligence about your environment, right? You could choose to only deploy like smart switches, and that would work, but then you are forced to only do manual policy, right? Because if you were to only use the smart switches, that's perfectly possible, but Hypershield would not have a source of intelligence to figure out what your environment looks like, and as a consequence, start suggesting shields against exploits and start suggesting segmentation, right? So if you choose to not have endpoint agents running, that's fine. The only consequence is you then need to define the policy manually, right? Now, deploying policy manually can sound a bit more of a challenge than it actually is, because Hypershield has fully API exposed. Everything you can do with Hypershield is also exposed through the API. So if you already have some automation pipeline or a CI/CD pipeline in place to deal with your security policies, it's going to be extremely straightforward to start plugging in Hypershield based enforcers, the smart switch, the VM, and at some point, if you choose to do so, also these agents, of course. The way these work, these agents, they actually are extremely lightweight, right? The main reason why we have these agents is we need to have something that allows the agent to realize how it should configure itself, what policy should be deployed on this agent, right? At the same time, we also need a way to share the local intelligence with the Hypershield controller, right? And we'll do that through the graph construct. And then finally, and this is quite important to realize on the endpoints, the actual enforcement of the policy, the data plane, if you wish, is done directly in kernel because of eBPF, right? So the agent is actually only running today every 15 minutes to spin up, build a new version of the local graph, like a new snapshot of the environment, share the local graph with the controller, and then also from the controller check if there is any additional policy to be deployed, right? And then once that job is done, again, the agent will not be doing anything for the next 15 minutes, right? Everything is being done in kernel. So then the network-based enforcer, a reasonably simple piece of technology, but at the same time quite powerful, because it is one of the many enforcers you can start introducing pretty much anywhere in your environment because it's a VM, right? And then what is new is the smart switch, right? So the smart switch is based on Cisco Silicon One for the hardcore packet forwarding. And then we have attached multiple DPU to the Silicon One chip so that we can optionally redirect traffic to the DPU to then do interesting things in the DPU, right? In the context of today's presentation, interesting things in the DPU obviously means Hypershield. So the way that this works is whenever the switch boots up, it will detect these DPUs, And then you can choose to configure those DPUs to be receiving traffic on a per VRF basis, right? So you can per VRF start choosing to redirect traffic specifically to a DPU or to many DPUs. And then inside the DPU, the Hypershield agent will be running. It will be configured as it would be like a network enforcer. It would connect to the Hypershield control plane. It would receive whatever network policies it needs to enforce. And everything's done, right? So from a deployment point of view, the way it would do, you do like 4 or 5 lines of configuration on the switch so that the switch knows how to make the DPUs call home to the Hypershield control plane. And from that point onwards, you manage those Hypershield instances running inside of the DPU from the Hypershield control plane. So why DPU? I think that's reasonably obvious. So there's different types of hardware platforms in this day and age where you can actually go and run software on. CPU has been around for quite a long time. NPU, that's exactly what, for example, the Silicon One chip is. It's like a network processing unit, like it's a piece of hardware specifically built to actually do packet forwarding. And then quite recently, both GPU and DPU have been gaining momentum. GPU is more in the hyper-parallel AI-based workloads, etc. And then DPU, we now start to see like an uptick because they're getting more and more interested or interesting as a platform to actually go and deploy software that needs to still have some enhancements to actually start more processing software packets in a fast enough pace to actually be able to keep up with whatever the network box is supposed to be swallowing. Now, initially, it's going to be a very specific type of customer that is going to be interested in these smart switches, right? The reason for that is if you look at what we can do with Hypershield today, it's essentially do segmentation, right? If I oversimplify and applying segmentation at the enforcer level, you're basically doing stateful layer 4 access lists, right? That's essentially what is happening at the enforcer layer, right? Obviously, there's a lot more to the overall picture, but inside the enforcer, inside the DPU, essentially that's what we do, right? We figure out what is the policy that we should be enforcing, and we enforce it. Now, for which type of scenario does the smart switch make sense today, right? Obviously, the amount of capabilities I will start deploying inside of the DPU is going to expand a lot, which will also mean it will become attractive to more and more customers. But today, the main use case where these smart switches make sense is those type of deployments where you need to have a certain level of network segmentation, typically because of regulations, because of law, because of assurance reasons, etc., which usually means some type of financial customer where they need to have an auditable minimum level of segmentation for all of their traffic, which usually means all of the traffic that enters the network fabric is steered through a big fat cluster of firewalls and then onwards to its destination, right? Now, one of the disadvantages of this is that, first of all, your cluster of firewalls needs to be able to be big enough, first of all, to deal with all of the spikes in network volume, right? That also means that you have big fat firewalls, which are usually not the cheap ones. And at the same time, these expensive firewalls, they're just doing segmentation, basically advanced network access list control, right? So from a value proposition, it's not that attractive, but it's a must-have. It's a mandatory checkbox to check, right? For those types of use cases, these smart switches are actually quite interesting because now you will have a distributed hardware enforcement layer, so you can actually distribute the enforcement, which means you can enforce closer to the source. You don't need to redirect traffic to a set of firewalls, and you will have network infrastructure anyway. So you just add now the segmentation capability directly to your hardware networking fabric, and you don't need to do redirecting of traffic to the firewalls. You don't need to manage those firewalls, etc. That's the value proposition of the hardware layer. The value proposition of Hypershield is that because, like I mentioned, now this, instead of having like a single segmentation enforcement cluster, typically a cluster of firewalls, it's now a distributed fabric. You need a way to actually make sure that the central policy is actually enforced across the entirety of the fabric, right? But like I mentioned, again, Hypershield does this pretty much outside of the box. So that's for the enforcers. Christian, any questions so far?
Yeah, I see you have eBPF coming up on the agenda, but we can take this one now just for you to catch your breath. So Martin is asking for eBPF support on Windows Server editions. Do we expect already available versions to be open to that new eBPF support, or will it be future versions of Windows that will offer eBPF support?
Yep. So I haven't seen official confirmation of this yet, but I anticipate it will be Windows 10 and above and Windows Server 2019 and above that will gain the eBPF capability.
Thank you. Martin, let us know if we did not answer your question. Thank you, Jerome. Go on.
Cool. So a quick detour to just highlight again the policy model that we use in Hypershield. So the main reason why we have, why we introduce, at least to Cisco and probably to the larger networking industry, a new policy model is simply because it's not just about policing traffic anymore, right? We want to do both segmentation at a microscopic level, like at intra-process level, at process loading library level, right? But at the same time, we also want to be able to use the same policy for all of the other Hypershield functionalities, such as exploit protection. So obviously we need a language or a policy description model that is able to do all of those things, right? At the same time, that model also needs to be able to readable and understandable by a human as well as a machine, right? So the way that we ended up with this model is we reused something that AWS released a while ago under the Cedar language, and it's essentially the PARC model, right? Principal, action, resource, with the optional condition. The way that this works, principle is essentially your source, resource is your destination, and the action is what is the principle trying to do with that resource. As soon as we have a match for that, we apply the effect, right? And optionally, there's a condition. So let me perhaps do this with an example that usually makes a bit more sense. We have, for example, this vulnerability from a few months ago where SSH has a vulnerability as soon as it loads a vulnerable version of the XZ library. So then you could say in human language, only allow SSH to load a non-vulnerable version of the XZ library. The way that you would describe that in a Hypershield policy would be, well, your principal is the SSH daemon. The resource is this library. The action is this process trying to load that library. Then we put a conditional in place saying, look, we're only going to match this rule if we're matching a library version that's vulnerable, right? So we know that 560 and 561 are vulnerable for this particular CVE. And then what we're going to do as an effect is block and lock, right? That's how you would put this in a Hypershield global policy. That's also what you would need to put as fields if you were to use the API, for example. You would need to create an object that you can then assign to the principal. You would need to create an object that you assign to the resource. You choose the load library as action. You put the conditionals as a version, a string for the particular library, and then you choose as effect block and lock, right? So that's exactly what would happen. Now, as you already understand, is that today we have endpoints which use different Linux distributions where we might have things like this, the policy like this, which is eBPF based. For network segmentation, we will have not just the endpoints, but we have the VM enforcer, we have the smart switch. In the near future, we will also have Windows. So of course, this global policy model will be translated into different implementations, right? So we will have, for example, on the right, this is the translation to the eBPF implementation that we get through Tetragon, right? So Tetragon can actually, as input, take a very readable YAML file describing exactly what we describe in the Hypershield policy, which will then be converted by Tetragon into an actual eBPF tracing policy, right? So there's like different layers of abstraction, but the nice thing is, as a human and as a programmer or as an automation engineer, we work with this Hypershield policy model, principal, action, resource, optional condition. Once we have a match, we apply the effect. So quite simple. So now let's do a small refresher of eBPF, right? So first of all, how do operating systems work? Well, we need this thing called a kernel, right? Because otherwise, all the different applications would have free reign on using the different physical resources like CPU time, memory, access to storage, access to the network. They might start consuming the entirety of a network port, which obviously is not what we want, right? We need instead somebody who will provide law and order, and that's what we call the kernel, right? So the kernel will have like a CPU scheduler to be as fair as possible to assign CPU time to each of the applications so that the applications cannot starve each other from CPU and other resources, etc., right? Now, whenever an application is requesting CPU time, is requesting access to memory, whenever it wants to read a file, that's what we call a system call, right? And those are calls that the application makes to the kernel. Now, eBPF is a kernel feature, right? This is important. And I think I stressed this last time as well. It's a kernel feature. We are using an existing kernel feature. We are not changing the actual kernel code, right? The kernel code in this day and age, I think, is probably one of the most complex pieces of code out there. So obviously, we do not want to start introducing change to code that is, one, complex, and two, critical to the system, right? You make a mistake, the kernel blows up, and the entire system dies, right? There have been examples in the past as to what the consequences can be if you start changing kernel code directly, right? Now, eBPF, the way it works is it's a kernel feature. And what does the feature do? It allows you to give mini programs directly to the kernel that the kernel will run inside of the kernel, right? So those mini programs, they will not run in user space. They will not run in the user layer. They run directly in the kernel. And they are event driven. That means as long as the event that triggers this mini program does not happen, the only thing that this program does is consume a few kilobytes of kernel memory, and that's it, right? And then whenever an event happens that is linked to that program, the kernel will run the eBPF program and then continue on working. Now, what can we do? Why is this so awesome? Well, first of all, we now have visibility into almost everything the kernel can see, right? And at the same time, we can also influence kernel decisions, right? So whenever the kernel says, okay, I'm going to forward this packet, you can now do, for example, access control, right? You can say these packets are allowed, these packets are not allowed. You can even do packet manipulation. So for example, you can say, well, this is a VXLAN fabric. We'll start adding or removing VXLAN headers or GRE headers or whatever, right? And this is where you might, for those with Kubernetes experience, this is one of the reasons why, especially in Kubernetes environments, this is so interesting, right? So obviously, network filtering, observability, network security policies, we can do all of that, all those things, right? So that's the beauty of eBPF. At the same time, eBPF is extremely performant, right? So I think I mentioned this last time, so I'll go reasonably quick. If you look at the worst case scenario, that's typically something similar to like compiling a big program. So here we compile an actual kernel, which triggers about 1.5 million syscalls, right? Kernel events. And keep in mind, eBPF is event driven. So every time a kernel event happens, that is a potential point in time when an eBPF program needs to run. So what we then did is we took as baseline, we measure the amount of time it takes to compile the kernel. And then we introduce an eBPF program that says for every single syscall, every single kernel event, write the raw data of that event to main memory. And then we see that the compute time goes up by 1.5, 1.6%. And keep in mind, this is a worst case scenario, right? In the typical working of a system, there is not going to be 1.5 million syscalls over a course of 500 to 600 seconds, right? This is really like a disaster scenario. So in real life, the impact of running eBPF is going to be a lot less. And then you might say, well, dumping into main memory and not just even manipulating the data, the event, that's easy. So let's make it a bit more interesting. And first of all, the raw data is now compiled and structured in a JSON data structure. And instead of writing to main memory, rewrite to disk. And then we see that the overall compile time goes up by 2.5 to 2.6%, right? And again, this is doing a quite intensive thing, right? So for every single syscall, we grab all the information, we compile all the information into a JSON data structure, and then we write it to disk, right? So that just goes to show that even in a disaster scenario, we see less than 2.5, 2.7% impact on the overall CPU time. So I hope that that illustrates that from a performance point of view, it's hard to beat eBPF. Then at the same time, eBPF is extremely secure, right? So people might think, well, if we start running scripts inside of the kernel and we add functionality to the kernel, are we then not bypassing all of the security controls of the kernel in the first place? The answer to that is obviously no, right? The people building and maintaining eBPF, a lot of them came to Cisco through the Överallt acquisition. They're actually smart enough to realize that, of course, we're going to make sure that that never happens, right? So first of all, whenever an eBPF program script is compiled before we hand it off to the kernel, it's going to go through a verifier to make sure that, look, none of those things, none of those violations can happen, right? Those scripts will not be allowed to do anything that any other programs would not be allowed to do. And actually, they're even more secure from a certain point of view because we do additional hardening before we execute the program. We then even execute the program in a very restricted, isolated execution environment, right? So only pre-approved data structures can be read, only pre-approved actions can be executed or modified, right? So it is an extremely controlled and extremely hardened and safe environment for eBPF scripts to run. Cool. Any questions on eBPF before I move on?
Nothing so far, Jerome. So I'll let you know.
Okay, excellent. Cool. So in this day and age, no presentation can be complete without talking about AI. What I'll try to do is answer two questions. Which type of AI do we use and why? And where is it used and what is the output and what's the end result of having AI in the first place, right? So to talk about that, first I need to spend a bit time about talking about graphs, right? You all know what is a graph. It's a bunch of nodes which are then interconnected with lines, right? And those lines basically show which resource is using what resource or is depending on what resource, right? So that's essentially a graph, nothing fancy. Why do we use graphs in cybersecurity? Well, there's many reasons, but in Hypershield, it's actually the core data structure that we use to deal with the huge amount of data that's now available to us, right? Because think of all the data that you're already generating just with your security tools, right? As an IT department, you'll probably generate even more data. So now by adding an eBPF capable tool, essentially every single syscall, every single event inside of the operating system now also becomes a data point, right? So that might be an avalanche that's just overflowing all of your data receivers. So we do like an initial layer of making sense of this, right? So instead of having like a raw dump of all of these data points, we're actually going to structure them in a graph. The cool thing about the graph is that it makes the data actually a lot more readable, both by a human as well as a machine. So that's again a big win-win situation to use graphs. Plus it will also allow us to condense the amount of data generated that we actually need to share to the control plane. So there's a bunch of advantages today. A key thing that I also want to highlight about the graph is sometimes people they start playing with Hypershield or they see some screenshot and they say, well, there's nothing new about this, right? I mean, we've seen graphs today and the graphs that I can see, that's all very basic. The key thing to realize is whatever representation of the graph that you can actually see in the graphical user interface of Hypershield is first of all just a minor fraction of the actual data available, and secondly, it's not how we show or visualize the graph visually to a human what's important, it's what's in the graph and how the graph is used by Hypershield as a system, right? So the way we actually build up the graph is it's an ontology-based graph, right? So that means that every single data point in the graph will have like multiple labels explaining what this thing is, right? Which is very meaningful for both, again, a human as well as for the machine, right? Because for a human, if you start looking at the graph, then you can see which data is in there. It's the data is described. This is a process, this is a file name, this is a file read, this is a path traversal. All of those things are in there, right? And then what the agent do is today that's like set to 15 minutes. That interval will most likely change and or be user configurable. Every 15 minutes, it will take a snapshot of the environment that it can see, right? What can it see? Obviously, all the applications running in that particular operating system. So it will create a graph representation of its local view of that particular operating system, and it will then send that graph to the Hypershield control plane, where we then have a merged service that will make a global view of your environment based on all of these individual graphs. At some point in the future, we'll also allow the network enforcers, so the VM and the smart switch, to start building something similar to a graph. Obviously, it's going to be a lot less detailed because the only thing that those enforcers can see is like network flows. But we're also looking into using that network flow information to contribute to the overall content of what's available in the graph, right? To have like a graph-based representation from a network point of view as to what's going on at whatever location that enforcer happens to be running. So why do we use AI, right? Well, obviously, if you just look at the sheer amount of information that we're now receiving from all of these agents, if you look at the sheer amount of CVEs that are being published every unit of time, as a human, obviously, we can't keep up, right? So where and how do we use AI in Hypershield today? Well, actually, in one very specific part of Hypershield. And that part is the bit that looks at all of this vulnerability information that's being published and then figures out how we can actually start creating shields for those things, right? So what that AI does, it takes as an input two main data sources. The first big main data source is a CVE database provided to us by Kenna, obviously. So now that AI becomes aware of every known vulnerability, we do a few things. We figure out how can we detect those CVEs to be present in your environment, and we figure out how can we create a shield for that CVE. What is a shield? I told you that would be wearing my technical hat most of the time, me using the term shield, that's my marketing hat. So what does a shield mean in reality? Well, it's nothing more than the marketing term for an eBPF script. What's so special about the eBPF script? The goal of the eBPF script is to prevent an attacker from abusing the CVE from being present in your environment, right? So for example, if the CVE is about a path reversal, it will prevent the path reversal. If the CVE is allowing you to do a remote code execution, it will prevent the remote code execution as soon as this eBPF script is loaded in the kernel where that application is running. And that's key, right? The only thing that we do is we introduce an eBPF script, and the CVE is no longer exploitable by an attacker. That means we're not touching the software whatsoever, right? You don't need to do software updates, software patches, software changes, anything like that. Now, creating this eBPF script, however, is easier said than done, right? Because first of all, we need a system that is able to, ideally automatically, as soon as this new CVE is released, create an eBPF script that is preventing an attacker from abusing that CVE, right? Now, there's many ways you can actually prevent a remote code execution, right? But how do we figure out which is the right way? There's a few things. First of all, we automatically check that after deploying the eBPF script, of course, an exploit of that particular CVE is no longer working, right? Now, there's many ways that you can prevent this. And this is where Talos comes in. Talos sits on a huge pool of data. And second of all, Talos organization has a big group of super smart, very experienced security professionals. So how is Talos helping us out? They're doing a few things. First of all, they're building an ever-increasing set of what we call ground truths. A ground truth is basically what is the right way to prevent this type of attack vector. Because lots of CVEs, the attack vector is the same, right? Some form of running a binary, some form of path reversal. So for all of those attack vectors, Talos is giving us, us, the AI, the proper way to prevent that type of attack vector, right? So that the Hypershield AI can actually use that as a way to validate that whatever it's coming up or calculating as a proposal to actually prevent the vulnerability is the right one, right? Second thing that Talos does is for all of the shields that we have, we already figured out how we can automatically verify that the shield is good at preventing the CVE from being exploited. But there is a second thing that is very important for us to validate as well, and that is to try and make sure that the shield is not going to prevent the operation of the application in the first place, right? So, and that is not trivial to do because we don't know what the application might be, right? Yes, there is a whole bunch of open source applications that are being used quite frequently in the industry, but there's also a whole bunch of closed source and a whole bunch of custom applications that are like homegrown that we don't know what the application will do or not do. So that's a quite tricky thing that we're still working on. And that is also the reason why if you look at Hypershield today, we have like 27 different CVEs that we can protect against today, even though we sit on a library of hundreds, probably even thousands of shields that are almost ready to go, right? The final stage that we're still doing is figuring out, is everything okay before we actually give you access to those shields, right? So that's where we are today. Of course, this is just good to know. You might have heard about Cisco CSDL, Cisco Secure Development Lifecycle, which is like a whole bunch of mandatory rules and procedures that anybody at Cisco that's writing code that's going to be put into customers' hands needs to adhere to, right? So don't hard code passwords, do input validation and all of those things. We also have now a similar framework for everything that any engineering team at Cisco that is using machine learning and AI models, right? So again, the proper way to do it, to make rules and regulations to make sure that it is never going to be cross-pollination, that we never train AI on customer data and all of those things, right? So also there we have like a whole team that is specialized on anything to do with ML and AI that is then going to make sure that all of the engineering groups at Cisco behave the way they should behave, right? And use AI responsibly. Cool. Then the next bit is to quickly talk about digital twin. Christian, any questions before I move on?
No, we're good to go. Thank you.
Excellent. So you all know about digital twin. It's essentially a way to still trust the system after what I just explained you, right? I now explained you that especially for the distributed exploit protection, a lot of the actions that you would end up taking are actually being calculated and generated by an AI, right? So why on earth would you trust it? Digital twin is our attempt to give the AI a fighting chance to convince you that whatever it's proposing you to do makes sense, not just makes sense in the context this shield is okay for this vulnerability, but this shield is okay for that vulnerability in your environment with everything which makes your environment unique, right? Your unique hardware, software, traffic patterns, everything. So the way that we do that is the digital twin will actually go and validate this shield or this policy or this new software version in your environment, in your enforcer, right? So if you have lots of enforcers all over the place, these things are checked in every single one of those enforcers. And we then generate a report that will actually tell you, look, this is what would happen based on what we've seen in your environment should you choose to deploy this policy, this shield, this segmentation rule update, etc. Right? And actually, I'll show you this live as well, but just a few things to call out. First of all, this confidence score is not how sure the AI is about something. This is a measurable amount of tests that have passed. And when we show you this test is passed, you don't just need to believe us on a word. We actually tell you exactly why we think it's passed, so you can agree or disagree with it. For example, we see that the minimum, the maximum average CPU, that's the difference between the active data plane and then what the digital twin has been testing, right? And then we say, as far as we are concerned, if it is within 5%, we consider it passed. But if for whatever reason you feel like, no, difference cannot be more than 1%, again, you have the data to make up your own mind and decide for your own whether or not you agree or disagree with each of these individual test results, right? But again, I'll show you this live in a minute as well. Let me keep track of time. Okay, we're nicely on time. So, and then also today, we are somewhat limited in reviewing network policy, right? So right now, the only thing you can see is the difference in hit count between the primary and the secondary data plane. In the near future, we're also looking to, for example, expose like IPFix or NetFlow style data, so you can see for those packets which are behaving differently between primary and secondary or primary and shadow, that you can see, okay, which traffic are we talking about, right? So that to give you that additional level of detail. Cool. And then before we switch to as you can see, I skip exploit protection and load segmentation because instead of slides, I'm going to attempt a live demo. So let me quickly talk about the API, right? So when we look at what does the architecture look like, right? So we have SEC as like the platform where the Hypershield control plane runs. That's also where you would navigate to if you want to see like the Hypershield UI, which also in a minute. But if you want to talk to the Hypershield management plane, the way you would authenticate with the API would be through provided you from SEC, right? So if you're already doing automating against SEC, you can just use the same token, your API token from your SEC user, and you use that to authenticate. So that's already an indicator that, look, the security cloud controller is like a common platform. This is not just marketing fluff, right? This is actually also the way we implement things in the backend. So even though we have like a dedicated Hypershield control plane management and all of those things, the way you interact with it, the destination, yes, this will be the specific Hypershield API endpoint, but not the SEC endpoint. But all the authentication goes through the usual SEC bits, right? So obviously, the räcker as well as documentation goes. I'm also getting close to start publicly deploying or at least releasing like some examples. Let me show you some of the example scripts. So that's, for example, a rendering of an empty OpenShift cluster, right? That is also already giving you like an idea of how much data there is actually in the graph, right? This is an empty cluster, right? For those of you that have been playing with different types of Kubernetes distribution, then you will know that OpenShift has a lot of additional capabilities, which translate into lots of additional process spots running all over the place. Now, the way that works is essentially relatively easy, right? So the script, basically, most of it is just setting everything up, right? You create import requests, you create your URL, an operation ID, an API token. I actually have like this tenant config. I have multiple tenants, so I can just give the name of my tenant, and it would then grab the token of that tenant. And essentially, the only thing that you do is you do a simple the data, just pretty printed on the right. So there on the right, you can see what the actual graph looks like under the hood, right? So you can see when I mentioned this is an ontology graph, what I mean, well, that's also CSCO colon some tables, right? For example, this is a host name, this is the machine ID, this is the debug information. etc. That is additional data that is being added to each of those nodes in the graph, right? A different example, you can list the shield. So again, everything is the same, but the becomes polysymmetrical. So show me all the shields that we have deployed, and then inside the shield, you will recognize, you will have this effect, don't allow, you will have the principle, the action, you have the resource, you have the conditionals, etc., right? So all of those things that we talked about earlier, they come in the API as well. Okay, so this is a Hypershield UI, part of SEC. So all I did, I went to Defense Orchestrator, which is now rebranded to SEC. And now let's go to Hypershield and let's start with looking at the policies. So as you can see, there's an active, a draft, and a history tab. What that means is under active, that's where you can see this is the actual policy that has been pushed. Under draft, this is where if you're starting to build additional policy that has not been tested or pushed to production yet, that's where this will live. And then under history, you can actually see all the different deployments you made or changes you made to your active policy in the past. And the nice thing is, if we then look at one of those policy pushes that have been happening in the past, we can still see the test report, right? So we can see, for example, in this case, if we go to the bottom, we actually added one policy. We added a policy which says as principal app service as resource, DB service as action, ICMP. So the action means establish an ICMP connection, and then as effect, permit and alert. And then what you can see is as part of the test review, we can actually see, look, these are the differences in flow age, this is difference in latency, this difference in memory consumption, etc. And you can see, look, for those that are within threshold for success, we say passed, and for others, we say, okay, look, we need review. Now, one of the things that we're still needing to clean up a bit is that if we introduce new policy, then we don't really have something to measure against, right? So then what do we measure against? Do we measure against the overall latency of overall packet processing? Do we look at the difference for those specific packets? That's things that we're still tuning. So that's why sometimes you will still see some funny numbers from time to time. And then also we say, look, we have different labels, right? So we say I have passed, we have failed, we have, you might want to review this, or this is something that we definitely want you to review. And this is also something that we need to, that we're actually going to address soon, because when we introduce new policy, there's nothing to compare to. So when we then compare a certain number with NA, we'll probably only put needs review when the number of hits for the new one is going to be 0, right? Because if it's 0, that means either your policy makes no sense because there's no traffic matching it, or you run the test when that traffic did not occur, right? So you might want to rerun your test if you're sure that the policy is correct at the point in time where you actually have the traffic visible, right? So that's in essence creating manual policy, right? Which is what we do today for the VM Enforcer and the Smart Switch. In the April release, we'll probably for the first time have policy that's going to be automatically generated by the system, right? So let me then switch to a different tenant where I can show you some other things. So if we then go to my tenant for the TME team, let me then show you the first bit of auto segmentation, which is what we call anomaly detection. So then if we go take a look at what are the workloads that we have, and by default, it will use a map. If the map is too big, it will tell you, look, you need to filter to something which is smaller. So if I, for example, reduce it to the Open5G application that I have running, then it will actually render the screen, right? So now if we go to the list and we go to containers, and here you can already see there is actually an exploitable host, but we'll do the exploit protection demo in a bit. If we then go, for example, and we take a look at the different containers, hold on. Visual TME, baselining. I just checked before. Okay, here we go. So we check here the pods, Kubernetes cluster. So you can see by default, something will go into baselining. Baselining is the mode it will go into as soon as we deploy it. As you can imagine, baselining means we're going to keep start building up the behavior of an application. Now, what is the behavior as far as Hypershield goes? Remember when I said we really use the graph data structure for almost everything? We even use the graph for behavior. Now, how can you describe the behavior of an application, right? That's a quite challenging thing to do, but because we have a graph representation of the application, meaning this application is these processes, these containers, these pods, it's loading these libraries, it's opening these sockets, it's receiving traffic from here and here. These are the processes that temporarily run, right? All of that, we have that in the graph. And then what we do is every 15 minutes, we create a new version of the graph, right? So if we run this for like 4 hours, then we have like 16 snapshots, and that gives us like a time-based view of the system, and this time series of graphs, that's a way to describe behavior, right? So that's what we're building up during the baselining. Then as soon as we go to scanning, we will actually start detecting deviations from the baseline, right? And these are actually quite subtle. So for example, what I did here is for this particular front-end pod, the only thing I did was a kubectl get environment variables. That's the only thing I did. So even just requesting to dump the environment variables, if that had never happened before, it will detect this as an anomaly. Different example is, for example, I think here we'll have some Java-based anomalies. So here it actually look, we detected inbound and outbound connections to the Java process, which we've never seen before, right? One of the things that we're actually going to do in the upcoming release as well is give more information, because right now it's still, yes, it's detailed, right? We're talking about a very specific process. We're talking about inbound, outbound, but we don't have the full view of those anomalies yet, right? So for each of the anomalies, we then have like a view of the, like a graphical view that showcases everything that's specific to the anomaly. But under segmentation, you can then also have like this view. Today, the only thing that we can do is like, okay, this is not anomalous behavior, this is good behavior, in which case we would acknowledge, which would mean we're going to add this behavior to the baseline. In the April release, we will have the capability to give the other decision, right? Where you say, well, this is actually not okay, this is bad behavior, generate policy, right? And then the policy that you generate might be, well, this is actually very bad behavior, let's go and block it. Or there might be, we want to take a deeper look, and then you might have, for example, a policy that says, for now still permit, but send a warning and capture information about the event, right? So April release is going to be the first release where we actually start to have the first bit of auto segmentation, right? Where we can actually, based on the information that we learn and the things that we see, start suggesting actual segmentation policies, right? This anomaly detection approach is the bottoms-up approach to auto segmentation. What we'll have soon after is the top-down approach to segmentation, where we actually start to propose actual macro segmentation zones, and then increasingly start to make the zones more and more refined, right? Then the other thing I wanted to show today is the vulnerability detection, right? So distributed exploit protection. So what I did today in my lab is actually deployed a vulnerable HTTPD container, which is vulnerable to this particular vulnerability. It will detect it, and then it will actually say, look, this is the shield that we propose to actually go and prevent this from happening, from being exploited, right? So then as soon as I choose deploy shield, and this is where doing a live demo is not always as easy. You can see it can take up to 15 minutes. Why does it take that long? Well, remember when I said the agent, it's not doing much. Every 15 minutes, it creates a local graph, shares it with the control plane, and then also at the same time, when it is talking to the control plane, it's also asking, do you have updated policy for me? So that's why this message says it can take up to 15 minutes, because if a few seconds before I clicked on the deploy shield, it did a check-in, then it will take 15 more minutes before we do the check-in, right? So one of the things I'm actually building on is doing like an in-depth recording where you can actually see me log into the pod. I will do with Metasploit, I will exploit the vulnerability to show this vulnerability is really there. Then we'll go and deploy the shield, and then as soon as the shield has been indicated as deployed, we'll try to run the Metasploit exploit again to show, look, this exploit is now no longer working, right? But because this takes up to 15 minutes, it's not so easy to do in a lab environment or in a demo environment. So that's pretty much my demo. So with that, I will conclude today's session. Let me see if I can perhaps put on the video again. So thanks a lot.